So, good evening. Welcome to the last week discussion on the NPTEL course Smart Grid Basics to Advanced Technology. So, I am Adyasha Sahoo from IIT Roorkee. So, the links for the slides and video you can get using the links given here. For the last week, the first topic that was discussed was basically demonstration of the concepts that we discussed in mostly previous week. So first was demonstration of energy management in DC microgrid. So here, can you remember whether we are studying a grid connected or isolated microgrid here? Can you recall whether this DC microgrid? So in this study, basically, we are going for a grid connected microgrid, a DC microgrid, not an isolated one for this case study, basically. So here you can see that this is the inverter, which is acting as a link between this DC microgrid and the AC grid, basically. So here you can see the AC side of the inverter. It is connected to the PCC or the MCB. Basically, this is acting as your AC bus to which you have AC loads connected here, right? And this you can say it is connected through a L filter. Then sensors are deployed here basically to sense this voltage and current. So these measurements are done using voltage and current sensors. So they sense the output voltage and current which will be used in the control algorithm here. Then coming to the DC side of the inverter, here you can see is the DC link capacitor, this one. So yes, this is the DC link capacitor here basically, and this is a microgrid connected to a variable DC loads here, right? And this DC microgrid, it is in the OpenRT platform. The control logic, it is done in the DSP platform. Then after getting the input from this voltage and current sensors about the AC side voltage and currents as well as the DC voltage VDC, the control logic will be implemented such that here you see the ABC frame components, they are transferred to alpha beta frame basically. So the AC basically you can say VABC and IABC using the class transformation. they are converted into alpha beta frame, and VDC it is as it is. You can see a VDC. After this, the control logic is implemented, which will generate the pulses basically to which will be given to the gate driver circuit of this inverters, right? Because basically this inverter is a collection of IGBTs, and this pulses will control the operation of this inverter using the gate driver circuit. So basically these, you can say, pulses through the gate driver circuit, they can control the operation of the inverters to get the desired performance. Okay, and what is this control algorithm basically? We will see in the next slide. So the control logic, it is embedded in the DSP platform as we studied. So basically, first we compare the DC link voltage, like if this was your inverter. So it is connected to the DC microgrid through this DC link capacitor, and here you have the DC microgrid consisting of DC source and loads. So first is the DC bus voltage control, because we know that this VDC should be constant for all times, right? So for that, we are comparing it, and the error we are minimizing using a PI controller. And this PI controller will in turn generate the desired AC side current. So you can see, to maintain the voltage constant here, this PI controller will basically calculate what should be the optimal AC side current, this IP star, and this will be again fed to the current control loop. So the current control loop will receive this information from the DC voltage control loop to maintain the DC voltage bus voltage constant. So when it receives the input from the voltage control loop, after that you see here, uh, again we get the alpha beta desired currents, right? And here you have the alpha beta reference voltages also information. And then using this PR controller, we will get the alpha beta desired reference for the voltage, which will be converted to the ABC reference. And after this, here you will get the desired pulses, which will be fed to the inverter. So these pulses will be fed to this inverter basically to maintain this DC voltage constant. So here in the laboratory prototype, you can see that the DC microgrid, it is realized using this OPLRT, where we are considering that we are the DC microgrid. It is basically consisting of sources such as DC sources. Do you remember what DC sources have been considered in this study? Yeah, true, correct. So here we are considering that we have a PV source and a battery energy storage acting as the DC source in the microgrid. And additionally, we have DC loads. So both of them compromise of the DC microgrid basically. So this part here. Then we have in between them, do you remember what is this component? This was the inverter, this one, right? Basically here this is the power amplifier, right? So here the information of the voltage will be given to the power amplifier, and the power amplifier, it will give its output as the current, which will be as a input to the DC microgrid. So this way first the information for voltage will go, and after that here we have current, so that we have a closed loop here, right? Then coming to this side, we have this inverter, which is realized using this semicron IGBT stack, right? Then we have some AC loads, such as this bulbs, which are connected to this PCC, which is realized using a MCB. Then we have this grid emulator, which will emulate the characteristics of a AC grid here, right? The characteristics of the performance of a AC grid. And then we have this controller here, DSP controller. So as you can see, the DSP controller, it is getting information of this AC side voltage current as well as the DC side voltage, and it will compute the PWM pulses for the inverter according to the control logic that has been programmed in this DSP, and accordingly this inverter operation can be controlled. So here basically two studies were performed, right? First case where we had considered that the DC microgrid is having excess power. So in the first case, the summation of, we can say, PPV plus P battery is considered to be greater than the summation P load, DC load in the DC microgrid. So since we are having excess power here, in this case we saw that the power was flowing from DC side to AC side. This was noted by a positive sign in the power amplifier. Then in the second case study, in the second case study basically, we were considering a energy deficit case. So that means the summation of PV plus the battery. So that was less than the load required. So in this case, we noted that the deficit amount of power, it was fed by the AC side to the DC side. and this was noted by a negative sign for power in the power amplifier reading. So these two case studies were studied. Then next we studied about the symmetric and asymmetric fault analysis of a DFIG setup, right? So this was the you can say some block diagram here. Just is my screen moving or it is still stuck in the previous one? I'll just reshare once again. Okay, so this was the slide. We were discussing about the fault analysis of a grid connected DFIG setup basically. So here the simulations they are being done in the RSCAD platform basically, and then uh, due to the different power ratings of these devices, we need to scale up or down accordingly. Here first we scale down for the GTAO card, and this is feeded into the power amplifier. The power amplifier, then it will, because here you will get very less amount of voltage, right, which cannot drive this. Basically this device is your device under test. If you remember for the previous lecture where we talk about uh, this PHIL, so there we had studied that we have a device under test, and so here the device under test is your DFIG. So to drive this DFIG will be of, let's say, 230 volt approximately, but the output here from the GTAO card, it will be less, which is not enough to drive this machine. So for that we need to amplify the power here in the power amplifier. Then this can be fed into the DFIG setup basically. Then up to this, basically you have reached to this DFIG setup. Then the output of this again DFIG setup. So up to here, if ahead of this, if you don't do something, any means if you stop here, then it will be a open loop. But for a closed loop, we again sense the output voltage and current of this DFIG, and we feed in back to the simulation system. Because let's say you want to carry out some operation for the device, right? Let's say for that you have given some command to the device, but it may not be necessary that the device was able to meet the target. So to sense whether our action, basically what we gave to the DFIG, was able to achieve or not, for that we sense the output of this device and feed it back to the simulation, so that the simulation platform can know what is basically the current output of the device under test, and that is done again through this GTAI card basically, and we have a connected filter between them. So this will close the loop for us, so that if the desired operation is not basically met, we can again give some command, or if basically it will be like monitoring this device. Then this was the laboratory setup basically. So you see here we have the RTDS racks are present here. You can see racks, these racks are there, and we have this cards basically which are mounted over this RTDS. So that is in the back side, so it is not visible here. And here you have this DSO to observe basically the waveforms. Then the FPGA based controller is here so that the control algorithm, it can be coded in this FPGA based controller. Like earlier we had used a DSP based controller for this energy management of DC microgrid. Here we are using a FPGA controller. Then we know two converters are there in D5G. So this is the rotor side converter, this is the grid side converter. And again this you can see here it is the DFIG and it is being driven by this DC motor. So this is the prime mover. And this prime mover operation, it is controlled through this chopper control method. So depending upon this chopper control, the speed of the DC motor can be controlled so that likewise the DFIG output can be controlled. So this is complete here. Okay. Then the first demonstration was for this GTAI card basically. So to observe the functioning of this card, first what we did, we have a function generator here and we gave some input voltage of 3 volts to this GTAI card basically. So you can see this is a 12 channel card, means it is having 12 pins or channels here you can say. Then after this, when this 3 volts of input is received from to this GTA card, through the filters, we then observe pass this to the real-time simulators such as the RTDS or the OpenRT. So basically, this will basically function generator. It is playing the role like when you receive the voltage or current from the power hardware device, which was basically our DFIG. So instead of getting the voltage and current output from the DFIG through the sensors, here we are directly giving this voltage through this function generator. So if you remember here, basically here the DFIG voltage currents were first. My cursor is visible, right? Okay. And then it was fed in through this GTA card to the simulator. So instead of this, now we have a function generator. So this function generator is directly giving this voltage here basically. Then for the, I think again the screen is stuck. Just give me a second. I'll reshare the screen. Ah, okay. I'll just reshare one second. So coming to the GTAO card here. So here we take the RTDS and then scale it down for the rating of this device GTAO card basically. So here also it is a 12 channel and this, so this is basically a physical, this you can see here, you can see this card is physically embedded or mounted on the racks. Then the output of this GTAO card is observed through this CRO. So here, if you remember this CRO in the previous slide, earlier it was that you got the input from the RTDS through the GTAO card and then it was fed to this power amplifier. So instead of this power amplifier and the DFIG setup, here we are directly observing what output we got here through the CRO. So here, basically this is playing the function of this power amplifier plus the DFIG setup. So here you can see the total schematic diagram as we were seeing. So firstly, we have this wind emulator. So to emulate the characteristics of a wind, we are doing this through this control of motor, right? Chopper control of this motor. So through this chopper control, we can vary the speed of this motor like your wind basically to emulate the characteristics of a wind in a lab setup. So basically this wind characteristics data you can feed in to this controller, like what speed or what characteristics of wind you want to emulate. So this will be fed to the controller and depending upon this, it will give the it will control the basically speed of operation of this DC motor, and this DC motor will drive the DFIG according to the wind information you have given here. So emulating the characteristics of a wind. So this was the wind emulator. Then as soon as the machine is driven, so the DFIG, it is connected to the grid side through this rotor side converter and the grid side converter. So we had earlier seen that to be able to deliver a constant amount of stator power, the rotor power in a DFIG, it is variable. So depending upon whether you are having excess wind energy, that is excess, if the P stator is excess, then the DFIG will consume the excess to maintain the constant power. Or if the wind speed is low, so that P stator is less than the required, then the DFIG will feed in the extra power so that you get a constant P grid here. So that operation is achieved by this two converters which are connected here. Then this we saw that how we had interfaced it with the real-time simulators through the power amplifiers. So here basically we then studied about the operation of this machine under unsymmetrical faults and symmetrical faults. So for the symmetrical faults, so if I come to the positive, negative, and zero sequence frame, so what component of voltage or current can be experienced or can be will be non-zero in terms of symmetrical faults? So symmetrical faults are balance faults, right? So we don't have a negative sequence component of current here. We only have the positive sequence currents. But in an unsymmetrical fault, it will lead to the presence of both positive and negative sequence components. Then next we saw the demonstration. अरे फिर से I think it has. So next we had saw about the demonstration of ancillary support from this DFIG, sorry, from the virtual synchronous generator. Yeah. So the next hardware demonstration was for the ancillary support from virtual synchronous generator. So if you remember in the previous lectures, we studied the operation of this virtual synchronous generator. So do you remember what type of ancillary services was being provided by this virtual synchronous generator? Anyone? Okay, reactive power. Any other support? So reactive power support it can provide, but while studying, we had we wanted another specific type of ancillary support from this VSG. So do you remember what was that? Like our concern was for another kind of ancillary support. So voltage, obviously it will be through the reactive power only. So here if you remember in the previous lectures, basically we were using it for inertia support. Basically, if you remember the concept of virtual inertia and also for frequency support. Although it may also give the ancillary reactive power support, but the study what we are doing was we were trying to derive the ancillary inertia support and frequency support from this virtual synchronous generator basically. So we had studied that due to this renewable penetration basically what will happen is your synchronous generators, traditional synchronous generators, they are going to retire. So these synchronous generators, they were you can say heavy massed mechanical systems, right? Those which could store the energy in their rotors and their mechanical parts. So, and as we progress to a renewable based system, so these synchronous generators they are being replaced by inverter based resources which are unable to basically the store the energy as a synchronous generator was able to. So what it will lead to is that whenever there is a disturbance in the system, so earlier what was that the case was that in case of a disturbance, the stored energy uh, that was stored in this mechanical parts of this synchronous generators, it was released instantaneously to basically manage the drop of frequency. So the synchronous generator stabilized that disturbance. But due to the lack of such support from this inverter based resources, it may lead to instability Whenever the renewables we are going, let's up to 40 to 50%, so such problem we'll be facing. So for that, what we are doing, we are including this virtual uh, this inverter-based resources by deploying this virtual synchronous generators to maintain the stability of our grid in whole. So here you can see basically the distribution system, IITR distribution system we are considering here. So there are certain feeders here, and we are having diesel generators. Then we are having solar panels deployed at various locations throughout the campus. Then we have batteries that we consider to be deployed. So the A location you see, these are the location for the batteries that we consider are being deployed in the system. Basically, why we need this batteries to be deployed? We have studied this in the past lectures also. So whenever we have renewables with us, that means we need a energy storage system to be deployed to handle the uncertainties and intermittent nature. So for that, whenever there is increase in this renewables, we need batteries with us. They can also provide reactive power support, which can help in voltage regulation. Then they can help in peak load shaving. That means they can charge and discharge it can be coordinated so that the peak load shaving is done, and they will help to provide uninterrupted power supply basically by storing the excess renewables and discharging whenever there is scarcity. So here, if you remember, we had 5 different locations where we are considering that batteries have been deployed in the campus. Then we consider that one VS virtual synchronous generator, so of 2.5 megawatt has been deployed. Then different loads are considered here of 7.8 MVA capacity. Then we have DGs, diesel generators in the campus, and we have solar PV panels at various locations. So, uh, do you remember whether this study that we are doing for ancillary support for virtual inertia, whether it was for grid connected or isolated mode? Anyone? So why we are considering the isolated mode of operation? Why not grid connected? Yeah, so basically grid is basically high inertia it is having still. So in case of grid connected mode, the grid will stabilize the campus network. So for that, we are considering a isolated mode of operation of this distribution system, basically because the isolated mode of operation, and here we are having high penetration of renewables. around 40%. So here, this in the RTDs, we are basically burning this campus network, IIT Roorkee campus network. Then in the FPGA based controller, we have the control algorithm that is being run through this FPGA based controller. Then this semicron converter, it will act as this VSG basically. And this for monitoring purpose, you have this screen which was showing the RTDS runtime window. Then this MCB, it will act as the PCC for protection of this power amplifier basically. So here I think two case studies were done. So in the first what was done in the first case study? I remember the induction motor load was varied. What was done in the first case? I am also unable to recall. Just give me a second. Disconnection of solar panels. Okay. So basically, first case study was where the solar panels were disconnected. So if the solar panels are disconnected, so that will be lead to drop in frequency, right? Because your generation will decrease, so the frequency will in turn decrease. So in that case, the VSG has to feed in the power and it will balance the stabilize basically, not balance the drop in frequency to normal conditions. Then secondly, the induction motor load, it was varied in steps. And here also we saw that the VSG was able to stabilize this. Next, we studied about the demonstration on peak energy management using storage devices, right? So here a typical load curve is shown and we have a PV profile. So as you can see, the peak generation, it is not coinciding with the peak demand. So what we need to do is we need to store basically this excess or surplus. We can charge the energy storage and store this surplus during peak generation. Charge in energy storage during peak PV or PE generation, and we can discharge that stored discharge the stored discharge this energy storage in peak demand here and here. So by that is what we mean by peak energy management. If we don't do so, then it will lead to voltage problems in the system. Basically, during these hours, in the case of high PV generation, you will face over voltages, and during these hours of peak demand, you will be getting under voltages. So for that, we need the storage systems to basically manage these peaks. So this battery energy storage system, they are an effective solution for voltage control and managing the intermittent renewables energy resources. They can help in peak load shaving by discharging the power. They can help in minimizing the power losses because of localized supply of power basically. And similarly, it can also help in decreasing the line loading in distribution system. So basically, if you remember the voltage control problem, so it is handled in two stages. So first is the optimization scale, and second is the control scale. So if you consider the time scale of operation, can you guess what will be the time scale of operation? Like which is in minutes and which is in seconds? Do you remember the hierarchical? Huh, yes, sir. I want to know that this voltage control, basically voltage, we want to maintain between certain range, which is basically zero point 0.9 to 1.1 at all times, right? So for that, we do this using optimization method and also by control methods. So what is the time scale of operation of these methods, I'm asking? Like which one is in minutes and which one is in seconds? Yeah, right. So, yes, sir. Right. So, in the first stage, what we do is depending upon the forecasted generation and forecasted demand, we run the algorithm or optimization model basically, and we receive the set points of operation for various devices in the system, right? The set points of various voltage control devices such as your capacitor banks for the OLTC, and also we can say the dynamic, or there may be synchronous condenser. You may get Q support from battery BESS or from your renewables. So these devices, they will get their optimal set points by running this optimization algorithm in minutes basically. After that, what may happen is, uh, let's say when you come to the real or actual mm, stage, right? So this was, let's say, t equal to minus 5, t equal to 0. So at t equal to minus 5, you had some information about generation and demand, considering which you run the optimization model and you get the set point for t equal to 0. But again, in real time, the forecast may change, right? So there may be variations. So this PG and PD, they may change to PG dash and PD dash. So if they change, then this, if the devices remain fixed at those set points, then it may lead to violations. So for that, what we have this control algorithms. So they act in near real time basically. So they will sense the voltages in the real times, and depending upon the control algorithm, basically QV control algorithm that we have, like troop based controllers. So they will change this set points to set point dash to manage this PG and PD dash changes so that your voltage is within the maximum and minimum limit. Okay, so this is how it is, the voltage management is done, you can say, in the system. So this real-time voltage variations, so they are done with the help of controllers, which may be your normal group-based controllers or they may be adaptive group-based controllers. So here the demonstration, instead of actual energy storage, actual energy storage, we are deploying or imitating its characteristics with this setup. So using this power amplifiers, filters, battery emulators, so these is acting as a battery energy storage, which is being deployed in one of the location of this distribution system. And this is again burned in this RTDS, and these are monitored using this RTDS, and this they are monitored using this voltage and current signals basically. Then coming to this various smart grid pilot projects that are running in the nation. So you can see here 3, 4, 5, 6, 7, 8, 9, 10, 12. Near about 12 pilot projects they are being run across the nation, and their location is given here. So what this pilot projects they are aiming to is, they are changing our conventional grid to the smart grid by adding certain features. What features? Such as advanced metering infrastructures, power quality management, outage management system, peak load management, and by adding distributed generations. So by adding these features in these pilot projects, our nation is progressing towards a smart grid system, we can say. So, the smart grid research and development areas. So, first, operation, control, and protection. So, the and operation and control of large and small scale renewables. Then we need to design the protection technologies also, as we had seen because of addition of this renewables, the conventional protection schemes, they are not able to function properly, right? Sometimes they may sense a normal condition as a fault condition because of the bidirectional power flow, so leading to false alarms. So for that, had seen that we are moving towards adaptive protection to build a robust, basically protection system in the presence of this renewable energy resources. Then we also saw about the wide area monitoring, protection, and control. So we had seen here that we need a situational, wide area situational awareness. Then we need energy management techniques. So here we had studied various techniques such as peak shaving, valley filling. So various energy management techniques we had studied in this course. So those need to be improved. Then supervisory control with the addition of multiple micro and nano grids. So basically the off-grid areas, they are being turned into micro or nano grids. So their operation and control has also to be managed. Then a network analysis and optimal power flow, because we saw due to this renewables, the grid is changing. So we may have a grid with both AC system and DC subsystems connected. So we need to do the load flow studies and optimal power flow network analysis studies for these systems. Then we need the modeling and simulation of large power grids, including the cyber systems. So we had studied that because of this smart grid, with the physical layer, we are adding a communication layer. So there may be attacks on this communication layer to threaten the operation of our power system. So here we had studied various types of attacks such as fault data injection attack, man in the middle attack, denial of service. So we need to develop a robust communication infrastructure also for this operation of our smart grid. Then seamless grid operation involving TSO and DSO. So as we know, these distributed energy resources, they are going to be mostly being added in the distribution system side, right? So their management need to be done by this distribution system operator. But till now, no body has been formed in India basically who can act as DSO. So there is ongoing debates like who is going to play the role of DSO in India. Basically, will it be the discoms whose roles will be upgraded to the DSOs, or we need the formation of a separate entity, separate body for the distribution system operator. And we also need the close coordination between this distribution system and transmission system operator for the smooth functioning of the whole power system, because this distribution system and transmission system, they can provide each other various services, and they can facilitate each other in basically managing each other power grids. So their coordination is also necessary. Then forecasting will be also very important, because we know this renewables, they are intermittent, they are uncertain. So we need to have better forecasting tools with the help of machine learning and artificial intelligence, who can better predict the renewable energies and the loads. Then we have distributed energy resources, storage and deployment issues. So we need various policy, regulatory, and market design, because no clear regulatory frameworks have been laid till now. So for that, new rules, new policies have to be amended, new standards have to be framed for the deployment of this renewables storage devices. So this is the need of the hour, framing of standards and protocols for these devices. Then demand side management with optimization and forecasting techniques for storage and renewable energy resources. So basically demand side management means controlling the demand or the load side, right? So controlling the operation of basically flexible loads through demand response activities. And this also will require the forecasting of these loads in the first place. So to achieve this demand side management, we need better forecasting techniques. We need better optimization methods which can effectively control the operation of this demand side resources for meeting the basically need of the grid. Then we saw the inertial issues. Basically, we were talking about this. So as the synchronous generators retire, the inertia will be a issue. So that we need to fulfill with the help of virtual inertia through these virtual synchronous generators. Then the optimal mix setting and sizing of storage at various levels. So basically the energy mix has to be decided beforehand through optimization methods. Then the sitting or placement of this storage devices basically, and the size that need to be decided, and these all can be done through optimization methods. Then electric vehicle interfacing issues. So we need standards for this vehicle to grid operation, grid to vehicle operation, because their uncoordinated operation will hamper the grid basically, because whenever they are large in number simultaneously, if they are charging, so it will threaten the operation of the grid. Then we need energy storage systems for meeting the transients as well as for the steady state operations. So for a grid with higher renewable energy resources, it has to be done with energy storage. Without the deployment of energy storage, we cannot move forward. So coming to the questions, High deviation in power in case of asymmetrical fault is mainly due to high variation in DC link voltage, high negative sequence current, high variation in speed, or high deviation in flux. Okay, anyone else would like to attempt? We got one high negative sequence current. So we discussed that in asymmetrical fault, it will lead to the negative sequence component presence. So due to this, there will be high deviation in power. So this is correct, high negative sequence current. It means which has been deployed in the field, you say? I see. And this virtual synchronous generator, it is basically type of energy storage, we can say, right? So energy storage which is depicting the frequency support which has been deployed for basically frequency support, we say, in very fast time scales. So that will act as a virtual synchronous generator. And if you remember the examples of utility scale deployment we had in week 3, so I don't remember the exact examples, but there were some cases where actually this energy storage devices have been deployed in the utility scale for frequency support. So you can envision that this is basically a special name that has been given. But in actual what it is a storage which is giving the ancillary support of frequency support. So that is being called as a virtual synchronous generator. But this storage, even if it is giving reactive power support, so then also it is a virtual synchronous generator. So if you remember, this is a type of hybrid energy storage basically, which was basically able to give a variety of this ancillary support. If you remember, there was 4 quadrants of ancillary support. So it was able to give a wide range of services starting from frequency, inertia, voltage, black start. So yes, so I hope it is clear. Battery energy storage, can you repeat? No, see, it has to be a hybrid storage because if you remember, the energy storage they were of high energy and high power type. So if we choose battery means we basically are implying to high energy type. So a high energy type of storage will not be able to give all these services. This high energy, are you able to get what I'm telling? So it has to be a hybrid storage with high energy and high power to be able to deliver this wide range of services starting from frequency, inertia, voltage to black start. So is this clear? Yeah, sure. Okay. Then the typical time step for this electromagnetic transient simulations is 10 to 20 milliseconds, 50 milliseconds, less than 50, less than 1 to 50 microseconds. So these are very fast time step simulations, right? Any guesses? Electromagnetic transient simulation. So basically, this RTDS, OPLRT, these PSCAD, RSCAD, these are electromagnetic transient simulation simulators. So they are actually very fast, due to which we do the transient studies on these platforms. Yeah, so we study the transient scale here, so basically 1 to 50 microsecond. So this is the correct answer. Then, for the transient study, the Powertronic converter needs to be modeled in small time step, average modeling, any of the above or none of the above. Anyone else? We got one small time step. Okay, another. Anyone else would like to attempt? So for a transient study, basically, we need accurate models. So if we use the average modeling, then it may not be give the correct results. For that, we use the small time step models. Which type of energy storage is suitable for peak energy management? High power density, high energy density. Okay, anyone else? Okay, we got anyone else? So we studied peak energy management, right? Where we were charging during high renewable, and then we need to store it, right? And wait till the period of high demand and then discharge them. So if you use a high power density, then huh. So if you use a high power density device, basically it may not effectively store this amount of power for a greater period of time. So for that, for storing this over a long period of time, we need high energy density. High energy density is the correct. This is for transient, for frequency response, because they can inject or absorb very quickly. So these are suitable for transient applications. So it is specifically for transient studies. Then in passive distribution system, voltage problems were mostly evident in head of the feeder, end of the feeder, across the whole feeder, or none of this. We got one end of the feeder. Anyone else? Yeah. So I have in passive distribution system where we are having this radial type. So just drop because ideally we consider that this is 1 per unit. So this delta V drop will add up, and this end of the feeder, it may get voltages which is less than zero point 0.9, which is the minimum allowable range. So for that, voltage problems are mostly evident in this end of the feeder. So basically, to tackle these, here we used to install the capacitors at those locations. Then in peak energy management demonstration, the grid emulator is acting as a DC source, AC source, storage, or energy storage, electronic load or storage. Okay, we got one AC source. Yeah, so it was a AC source along with some other components. It was depicting the function of a storage. So it was not alone acting as a storage. There were other components also. Then, do you have any doubts for this week? We have plenty of time with us. Yes, sir. So this is the end because week 12 we are wrapping up. You have to go through like actually there was an option for one extra session, but the date has passed and I had not filled for that. So this time I may not be able to help you. But some other TA may have opted. Okay, okay. Actually, this last date was passed. It was some 12th, and since last week, no one got told me so. Okay. Yeah, this was my first time with this course. No, sir. Actually, the paper it will be set by other set of TAs. So there will be, I think, some other TAs with you. Those are the course TAs basically. So they will be responsible for framing the questions for your assignments and for your exam papers. So if you have any doubt regarding the examination type and pattern, they will be able to clear. We are not responsible for that. Yeah, and I think they are MCQ type only, the exam pattern, and they will be in accordance with the assignments. When do you have the exam exactly? 29th. Okay. So 15 days time. Oh. So I, yes, sir. Okay, if anyone has not any doubt, I wanted to discuss just one last concept maybe. So uh, throughout this course, basically, we were talking about transforming the ABC frame to alpha beta frame and DQ frame. So I just wanted to give a heads up that what this is actually like, what is the transformation that is we are doing. So if I draw the phasors for this ABC, so this is your ABC frame of reference, right? So after this, when you convert this to alpha beta frame of reference, basically this is your alpha beta. This is your beta axis and this is your alpha axis. So if you want to convert uh, this ABC frame to alpha beta frame basically, so we need to multiply it with a matrix, which basically is the Clark's transformation that we have been talking about. So if you see, this alpha axis is coinciding with the axis of A, right? So if we just a second. Yeah. So, so this alpha axis is exactly coinciding with the uh, axis of A, right? A phasor basically. So this alpha to A will be 1. And if you see beta axis is not with this A. So here we get 0. And similarly, uh, here this B, if you decompose it into sine and cosine part basically, so here if I do it this way, so the alpha will oppose it. It is in the opposite direction of alpha. So it will be negative, and for beta it will be positive. So it will be in sine and cosine of 60 degrees angle. So hence you get these values, and the direction will tell whether it will be positive or negative basically. And then lastly coming to the C again. So if I decompose, then it will be negative for both. You can see it will be opposing both this alpha and beta axis. So this was according to their direction. Then to balance out their magnitude, we need to multiply it with the factor of 2 by 3 basically. So this is how you transform from ABC frame of reference to alpha beta frame of reference. Next, coming to the DQ frame of reference. So, so this D and Q axis, if you remember your machines concept basically, so these are these axes. Let's say this angle is theta. So again, if you want to convert this alpha beta frame to DQ frame, basically you will be getting sine and cosine terms. So basically, if I decompose them, so here you will get cos theta and minus sine theta. Similarly for beta, if I do it, it will be positive, it will be sine theta and cos theta, where this theta is angle between your alpha and d axis. So this is the transformation between this ABC to alpha beta and alpha beta to DQ frame. So I hope this was clear. And any feedbacks or anything for the course, we have time with us. So what is the last date for the assignment of week 12? So that will be depending upon your control algorithm. So depending upon this control algorithm, it will depend which one you want to take. If you go back and see the control algorithm figures, so it will be sometimes you are comparing the reference with the actual in terms of alpha beta frames and sometimes in terms of DQ frame. So that, mostly. And for PI controllers, I think it was DQ frame. Yeah. The last assignment when you need to submit the for week 12. Uh, what is this due date? Okay. And for the exam, you need to go to physically to the center, exam centers. It is that way, right? And the duration is for, oh, 3 hours is a long time. So considering that all will be MCQs, mm, all are MCQ. Acha, 50 questions. 50 questions, you are getting 180 minutes. Okay. Okay, then any feedback for this course or for like my sessions? This was my first time experience, so thank you, sir. If any doubts for any of the week, if you can recall, we may take it up now. Hmm. What is the question, sir? Can you repeat? Okay. Huh. But the answer was answer. Okay. I yeah. Yeah, because now if you see mostly this inverter technology based your ACs and refrigerators, but they are coming up right now. But previously, if you see the design, all our loads are AC, like induction motor type loads. So obviously DC will be efficient, but if in the current scenario, again, if we have to go to DC, then we have to change basically the consumer pattern like type, or we have to go for extra converters. So in the current context, it is given as AC. But if you theoretically, if we compare this rate regarding that what is going on now, it will certainly be DC. So this AC and DC, it is heavily debatable topic that which is better. In the middle area, we were sure that AC is the better one, but now again, this debate is there that which is more efficient type, whether it will be DC or AC. So we'll see it in near future if we are coming to a conclusion or not. Yeah. Hmm. Yeah. But again, if this DC microgrid concept is coming for these reasons only, because our source is also changing to DC. Ah, true. Because if you see the AC industry side, majorly they are located in the sub-transmission level, which is the AC side. But so there is transmission, some transmission, and there will be distribution, or that is we call medium and low voltage. So the microgrids that we are talking about, DC microgrids, they are certainly in this low voltage side. And mostly the big industrial consumers, they are directly connected to this sub-transmission level. So for this, if you then we are turning our system to basically hybrid AC-DC type, for which we were discussing the load flow algorithm for such a infrastructure grid. So we may realize a system where we have a mixture of AC system and DC system being connected with the help of converters. So different power system studies we need to carry out for this hybrid type of systems, because earlier we were prepared with this AC type of systems. All power system studies, they were for this AC type systems, but again with the changing of this topological basically infrastructure, so we may have to develop the power system algorithms accordingly. So we are moving towards that. Any other doubts if you recall? I am in my third year basically, so I don't. No, it is not fixed there. So uh, I don't know when I'll be wrapping. Mostly I expect by 5 years. So my area was on this optimization. If you remember, we were talking about this point here about seamless grid operation involving TSO and DSO. So my work is the coordination of both this to derive the ancillary service between these two entities. So the ancillary service provision between these TSO and DSO using Basically, it is optimization algorithms. My work is focused on this, if I pinpoint. Some have joined now. So if you have any doubt, you may raise your queries now. Haha. Hmm. Yeah. Yeah. It will be basically the multiplication of both this, right? And this we don't do physically in the MATLAB and Simulink platforms. So basically, there are blocks for this. So just if you uh, call that block, it will have the inbuilt function. So you give them the ABC and they will directly transform it accordingly to alpha, beta, or DQ. And if I basically, if you want the direct relation between them, so alpha, beta to or ABC to PDQ. So this will be basically multiplication of this, right? Because this alpha, beta, this will be replaced by this, right? So if you multiply this two, then direct multi. So that way. Okay, someone just asked that second question of MCQ, like the one we discussed today. One, two. This one. Are you talking about this one, Kushi? Yeah. So, do you have any doubt here? So if you remember, we studied that this Simulink platform that Simscape platform we are using in this MATLAB. So we cannot, it's basically computational ability is limited. So for going for larger systems or for high resolution, like in microsecond studies, we need high computational power, right? Because the algorithms need to run in this time scale. So for that, we are going for this RTDS and OpenRT platforms, which are electromagnetic transient type simulators. So these are having high computational ability, which can process this much amount of information in this amount of time, so that you can get a flavor of what the practical scenario will be after deployment, basically. So these are widely tested before the field deployment. So this PHIL simulations, basically, before actually integrating it in the grid, various types of studies are conducted using this PHIL simulations to test the device, that how it is going to behave under various scenarios. And finally, when it is able to pass all the tests, we then physically deploy in the distribution system so that we do not face any problem. So with this Simulink, we cannot tell that how it is going to behave actually in the practical scenario. So for that, we are using these simulators. Okay, any other doubt? So this last, if you wanted one extra session, so what content you wanted to discuss? I may ask the portal organizers. I'll request them if they can provide me with one. Okay. Oh. Hmm. Okay, the 120 question. I get your point. So, okay, sir. I'll try. From the nodal center, we received one mail that if you want to schedule, but we had to fill some Google forms, but the last date has actually passed. It was on 12th, I think, the last date. So I had not filled it up previously, but still I request them by mail. So if they allow me, then we can meet in the next week and we'll discuss all the questions, like MCQ questions of all the weeks in once. But yeah, yeah, sure, sure. If they allow me, I will certainly let you know, or they will let you know of this extra session. I'll give my try and I'll mail them and request them. Okay. Anything else? Or we'll, okay, even we may not meet in the next session. It is uncertain. So I will wish you all a very best for the examinations so that you get your certificates and hope that you were able to learn something through this course. And okay, thank you all for this participation and for giving me this experience basically. So without you all, my experience. No, sir. Okay, let's see what is happening. So, anyways, I got to learn also from you all. So, it was nice experience. So, thank you all. I think we'll join then. We will close the meeting then, if no. Thank you for joining. Thank you, sir. Thank you. Thank you for joining. Thank you. Thank you.